This is my recent favorite quote. I mean, no matter what we do, right? We want to store energy, store information, convert energy, convert information to energy, and we always face interfaces, right? There's applications from batteries to fuel cells. This is ionic electrochemical RAM to store informations, and solar. Recently become a chemist, started working some organic synthesis. And this one maybe look out of space, like this is engine block, aluminum engine block. The point is, it's not aluminum. It's not at a thermodynamics equilibrium, because if aluminum's at its thermodynamics equilibrium, it should just become oxide. The point, we have a big chunk of engine. I worked in GM before, so we work on engine blocks, and so because the surface can passivate and form this oxide layer. And no materials that really just function in vacuum. So I work on interfaces. And the interfaces of the properties are also coupled. So all these devices, you break the interface, and then the electron cannot pass through the interfaces. We have a dead device. And so the mechanics property is important, and the mechanical properties are always coupled. So my early work, when I think about interfaces, I often describe how does lithium goes into electrode and out, and how does that change the volume, and that causes some failures. This is a deliciate silicon. This is a deliciate silicon. This is deliciate fast. This deliciate slowly. So we got more lithium out of this, but even that, we can see some interface delamination. So when I treated these problems, I think the lithium inside of this electrode, we treated them as atom. Right? It's not electrochemistry. And today here we're talking about electrochemistry. And electrochemistry is how the electron ions meet and separate. I think in batteries, you heard a lot about batteries from Monday and today. Batteries, whenever battery fails or battery degrades, just because the electrons and ions did not meet at the right place or the right time. Right, so look at this. This is a lithium ion the lithium ion goes from solvent across this interface passivation layer and landed on the lithium electrode and meet with the electrons. This is a perfect lithium ion transfer reaction, won't happen every cycles. However, if the electrons did not stay here but to go to the electrolyte, and we have electrolyte decomposition, you heard a bit, that's kind of lost the electron in our battery. Or this is a solid electrolyte work. So this is like polycrystalline, like synthetic powders, like lithium, lanthanum, zirconium oxide, which is one of the solid has very fast ionic conductivity. But and because they are sintered particles, you have defects. You have grain boundaries, pores, and pore surfaces, and those pore surfaces can trap some electrons. And I have your interesting discussions. The electrons may not stay in the liquid long, but they could stay in the solid long, and then they can reduce the lithium. So you have some lithium metal inside of the electrolyte, and then when they connect it short the circuits. Right? So that's the example that lithium and the electron did not meet at the right place. So the lithium, the battery application is one of the applications where at this interface we have multiple competing reactions, right? And the electrolyte is very complicated. As you heard from the talk before lunch, there are so many things you put in, we get salt and solvent, mix the solvent additives. And commercial batteries, they may have at least 10 additives there for different purposes. this is a new project we're involved in thanks for the NSF Center for Synthetic Organic Chemistry. We're trying to make new molecules out of using electrochemistry. And like this is an E-Birch reduction reaction, which actually simplified many steps. Now let me do one step, one-part synthesis. The good thing is it's one-part synthesis. The bad thing is it's one pot. How many things in that pot? You get the salt, cation ion, mix the solvent, and the things you want to reduce and things that is other purpose, like things they put there. It's really a multi-component system. Right? I think I'm a little bit lucky that I don't have to deal with water, which is so complicated. So we're dealing with organic solvent, but we just have many of them. And so when you have so many species in the system, what comes to the surface is the first question I want to answer. Right? And then after that, we can just think about how do they competitively react at this interface, and what are the products. This morning we have a talk, reduce the particle went away, luckily. But in this case, the reduced particles can form a passivation layer on the surface. And this layer, we want them to transport ion but to block electron. And this layer, we can't really block electron because we continuously have the electrochemical reaction, but we also want some partial protection of the surface. There are some porous, porous protection layer is needed. So the surface design and the electrolyte design is very important. And so I'm not going to talk about bulk electrolyte properties. I'm going to focus on this electrolyte near this interface. And we'll start from batteries. We'll just have two examples to show at the end for the organic synthesis projects. So we said every cycle we want the lithium and electrons come back and forth through this interface. But if the electron leaks out from this layer, they will start to attack the electrolyte. And then that causes side reactions. Every lost electrons is the lost electron that cannot combine with the ion that we want. So we're going to talk about a very complex electrolyte. The first thing I kind of moved from the material science field to the battery field or is to learn some electrochemistry. I totally agree with Axel's talk on Monday that the electrochemical equilibrium condition needs to be clarified first. So I'm going to talk full cell and half cell to find out what are the potential on the electrode. In materials materials project, so on average, right, we're talking about the overall thermodynamic driving force for a battery is the chemical potential difference of these lithium species from one phase to the other, right? So lithium to lithium cobalt oxide. You can calculate from DFT, you're right close to the truth and experimental values for volt. But if you measure electrons, right? If we measure electrons, if this is a band level of the lithium, this is a Fermi level of lithium, this is the lithium cobalt oxide. If you take a look, if the electrons level is about 2 volt difference, not 4 volt. Okay? And that's because those materials are separate. Right, so if I have separate the lithium cobalt oxide, the Fermi level difference is about 2 volt. It's not open circuit voltage that measured as a 4 volt. Right? And so Michael Swift and I worked a while back in MSU. We just try to describe this equilibrium condition. The lithium ions need to reach equilibrium because they can move from one electrode through the electrolyte to the other electrode. So when we reach the open circuit condition, and the ions have to achieve its equilibrium in terms of the electrochemical potential of that, and that is related to the chemical potential of the atomic species and the electrons' electrochemical potential. right? So this we already calculated from our DFT. That's from this is 4.2. We know how. And this one, we know it comes actually two parts, right? It contains this work function difference from pristine material and the electrostatic potential, right? So from theory, this need to be balanced. Therefore, this, when we connect this in the cell, this need to change, right? So what's going to happen is we must have a net, electric potential difference between electrostatic potential, the difference between our cathode and anode materials, and that will shift the electrons' electrochemical potential level to be equal to the open circuit voltage, and that's the 4 volt. Right? So here we can estimate the difference of the two. But this full cell description does not give us the information about what exactly this phi is at one site. So we have to think about half cells, right? Half cells, I would call this as what potential we should call this. Make it more confusing. We're trying to look at this reaction. We're looking at this reaction at its electrochemical equilibrium. So I would not even call this, people call this reduction voltage of lithium, but I think there's an intrinsic difference. Is because the example you see this morning again, the ions get electron and then would stay in the electrolyte after the reduction. But in this case, if we have this reaction, the lithium has to kind of becomes the part of the metal, right? So the cohesion energy agree is important. So we kind of modified the Born-Haber cycle a bit. So we say we want to really know this energy difference of this reaction. You can argue my calculation numbers can be more accurate, but the first level of approximation is the cohesive energy is now replaced by a vacancy energy. If I take a lithium out, I have to create a vacancy, and that the vacancy formation energy. And material science typically put that atom back to the bulk. So here we're going to take this atom to the gas phase, and then we're going to split this electron ion, and that's the ionization voltage, and then we're going to put the electron back, and that's reverse of the work function of the lithium metal, and then I put the lithium in the solvent, and that's solvation energy. After this, and we can see that in this charge neutral status here, and this lithium ion is very energetically stable inside the electrolyte, right? So that means this is delta G0. I hope this notation is right. And we really, with first level of the approximation is we have to shift these electric potential up on the metals, lift the Fermi level, so we can make the lithium ions energetic level in the liquid phase and the lithium metal in the solid phase at the same level. This is electrochemical equilibrium, and then my electrons is already here. And this actually gave me this nice relationship. So for me to rethink about how do we align all these reduction potentials, and this is my lithium, and it's not too far from the this table that Stochasticity table everyone use. I will talk about its problem later. And then we also did this for magnesium, and it's slightly voltage reduction voltage for magnesium slightly below the lithium, so we're not too far from experiment either. Right, so this energy electronic level, Fermi level electrons is necessary for us to align that with the electrolyte reduction voltage, right? So electrolyte may start to react here, so therefore those will be not stable, right? If you're operating the battery at the lithium reduction voltage, the electrolyte will be reduced. If a electrolyte reduction voltage is above the lithium reduction voltage, and then the electrolyte will survive. So this will allow us to kind of really compare the reduction voltage of deposition and electrolyte decomposition. And what I want replace is basically this table, because this table is measured in aqueous. And if we change the electrolyte, and everything changes here, right? So if we align everything with respect to like our vacuum and our electrons, and I no longer need this. Okay.
I just have a question.
Yeah.
Maybe not. I don't see any losses dragging your ions across.
Not yet. That's the kinetics. This is thermodynamics. Okay. So it's true that you can see that the measured reduction voltage for lithium deposition really changes in different electrolytes. If you see the same color, there's the same electrolyte at different concentrations. And this is their Coulombic efficiency, CE, so that related to the energy loss, electron you lost to react with electrolyte. So the two things are competing. So we have to find like a common reference to study all these competing reactions. So that's thermodynamics. And we did actually need to come up with the kinetics. So eventually we built this like cell with about 1,000 atoms, like lithium, a passivation layer, and some 32 EC molecules, and then we look at the energy difference of the ion and when the ion kind of stayed in the lithium metal. We look at the energy difference of that, and then the more ions we put in the electrolyte, and the more electrons we left on the lithium metal. Eventually, we can see that the electrochemical equilibrium condition and how much charge density I have to have on this lithium metal. This will simplify my other calculations later, right? I would need to calculate the double layer, and I need to know the potential minus the potential of zero charge. I think Wolfgang Schmickler's work has been mentioned multiple times in this conference, and he actually used our DFTB parameters and did some calculations. And he also pulled out this table and said, look at this deposition voltage here, and this is the potential of zero charge, and the lithium, sodium, potassium, they're all below, more negative than the deposition, than the potential of zero charge. If you deposit the copper or silver, you actually deposit above the potential zero charge. This is really interesting, but this is measured in aqueous, it's not inorganic, right? So we need a whole lot of calculations and a framework to describe the complex electrolytes for batteries. When I did this work, so I did the kinetics barrier for this. I'm not going to talk about that today, but when I did this work, we started to notice that, right, when this lithium is charged, even though you have some passivation layer on the surface, and those molecules, these EC molecules has already reoriented, like almost like form this strong dipole on the interface, and this is above the potential that we deposit lithium, right? This is surface charge is here, right? So I fully believe that whatever I do, I need to simulate this charge interface to really understand electrolyte. So we start to get into the electrolyte design business. This is kind of like my lab, virtual lab, not a high throughput, but we have some different salts. And we have some different solvent. So in the lab, you will mix the salt and to the solvent, and then you can add some additives. Where's the additive? Like this is an additive. You can add this few molecules, those things, they are liquid. They do not solvate the salt. They have really limited solubility for the salt. And so they will form more interesting structures, I'm going to say. So electrolyte design is not just the chemistry, It also have compositions, and also I'm going to explain as beyond solvation structure, we have even more complex nanoscale structures. And that is because we're start dealing with more complex electrolytes. So you can mix salt and the solvent. And so this is a material science way to present electrolyte. So if we're dealing with a very dilute electrolytes, we're increasing our concentrations, we're reaching our solubility limit. And different solvents, you may have different solubility limit, right? After you make this high concentration electrolytes, and they don't flow well. And so that's why this diluent was added and try to make things flow better. And so then you get one part, you can start to add something else. And so this concentration will start to follow this line, right? And so this is like one way to represent the chemistry and composition design space, right? Okay, so this is my workflow. So we have a pot. So remember that 32 EC molecules I had before? I did tight binding calculations. That's actually as a fake electrolyte, and EC is not even a liquid in room temperature. It have to mix something, a co-solvent, to make it liquid, and it become liquid also when they solve it with salt. And so we want to model the real electrolyte, the real composition. So we'll do classical MD simulation, make sure we can recover the bulk properties. And then we subject it to two slabs. We use constant charge just for quicker calculations. And we want to see what comes at this interface, what are the probabilities for all this clusters. And one thing you need to know that these molecules' reduction voltage increase dramatically when they're next to a cation. EC reduction potential, probably you calculated 0.6 EV, but if it's next to lithium ion, it becomes 1.6. Right, something like that. So we really need to look at this solvent molecule, whether they are bonded with lithium or not, right? So we calculate their probabilities around this lithium, and then we calculate their reduction reactions. And then this is the probabilities of them appear in this 1 nanometer range. And assume that everything in this 1 nanometer probably have a good chance to get electrons. And that's electron tunneling distance. And then eventually over time, it's going to be reduced. So we just count their these chemical compositions and probabilities through this way. This is like a simulated CV, right? So we lower the voltage, and the things that will start to decompose and get electrons. You go lower the voltage, more and more can be reduced, right? So this is, I leave all the equilibrium in this, and then I'll leave some kinetics to the other things to simulate the build up of this layer. And so recently we developed, we pull out the kinetics from the FT calculations and then give those information to phase field model. We can simulate ACI growth, multi-layer growth from nanoseconds to a second until it's saturated. We will not talk about that today, but we'll just talk about thermodynamics for a bunch of different electrolytes, right? Localized, low concentration, high concentration, localized, the high concentration. We'll give some examples. What do we think? These are two classical electrolytes. One is used for carbon electrode, one for lithium electrode. And lots of people want to have fluorine species. If you just have salt, and the solvent, you notice the fluorine species only comes from the ion, right here. And they we can talk about why we want some lithium fluoride in these surface layers, but bottom line, we want some fluorine species. These two solvents are very different, and this solvent has really high dielectric constant, and this has very low dielectric constant, right? And then if if the ions cannot contribute to the fluorine species, we often add another like additive, FEC, fluorinated ethylene carbonate, to contribute to fluorine. And so this is the additive. So we look at this with, without the additive. Interestingly, right, you think about it, you have negative charged surface, and we want the negative, the ions to come to the surface. They should be repelled away, right? In this strong solvent, what we found, we count all the different species. What you really want to focus on is this orange color, and that is the ions. They didn't show up in this strong solvent. In the weak solvent, and because we have ion pairs, when we attract some positive lithiums, we do attract some ions to the surface, and all of the ions are lithium associated. And so that's tells us you will have fluorine species in this near this interface layer, and this one you don't. The other thing is the solvent itself, right? The EC solvent themselves will decompose right here. And this one, these two solvents will not decompose as a free solvent, but if they're bonded with lithium, they will get reduced. All right. So overall, we have more electrolyte reduction for this one, but much less in this one. So now I want to add this additive. All right, I wanted to add this FEC because FEC has very strong binding with lithium, and so they just show up in the double layer region and get reduced. And this one's interesting because FEC also come to the weak solvent to the double layer, but they kicked out the ion. So if we look at the fluorine species, we didn't see many change, right? The composition have changed, but the contribution to a fluorine species and now changed from ion contributed F to the FEC contributed F, right? Right, so there are some like immediately obvious conclusions of this, and this double layer composition is also very sensitive to temperature, right? I didn't know this. So this simulation I showed you before is 20 degrees C. If I have the ions without the additive, if I only freeze this to -4, it didn't freeze. This is like, I run this at minus 40 degrees C, those ions left, right? So we actually don't know too much about this. One of this is probably related to this temperature dependent, right? So if, I don't know how to think about this. My first impression is at lower temperature, the molecules become more frozen. They cannot shelter the surface negative charge well, so the negative ions get more repelled away from the surface. But I don't see any monotonic dependence on temperature in terms of the balance and for this, right? So you can imagine that, yes, please. Then in this case, I really need those FEC to provide the fluorine species, and this one I don't have to. And then as you run the experiment, you see at room temperature, adding FEC or not doesn't matter that much. At minus 40 degrees C, yes, right? So we later on we also can correlate this with the like elemental percentage in the ACI layer. So previously we first worked with Matt McDowell's group on this. We did the bulk calculations. We have no correlation of their experiments. And then when we did this surface double layer calculation, it surprised us, right? So let me move a little bit more complex electrolytes, right? So we said the previous electrolytes were like 1 molar, so about here. And so this is like 1 to 10 ratio of lithium ion to solvent, right? So if we increase the concentration up to here, 1 to 1.2, that's about a 1-to-1 ratio-ish, the salt and the solvents. Really, there's like a lot of aggregates of the salt and the solvent, right? So, so that is the salt and that's solvent. And this molecule, I'm not a chemist, so I don't know the names, TFEO or something. This is actually quite interesting. This is a quiz problem. It has very similar dielectric constant with the solvent, but it just does not solve the salt. You can see the salt in this TFEO is a cluster, right? So all these are MD simulations. This is about maybe 3 to 4 nanometers wide. And then these two, because they have similar dielectric constant, they mix completely, right? I have one question: why this one solved the salt and this one does not? They have similar interactions with lithium, right? So it turns out, oops, what happened to this picture? Okay, so that's supposed to be this picture. So it turns out that we can pack a solvation shell 1, 2, 3 DME around the lithium, and then we can solvate it. We can take it out from the binding with the ion. But if it has a TFEO, if you see this molecule, they are really big, right? We packed 1, we packed 2, we could not pack the third one, right? So if you see there like solvation structures, right, the third one can't go, right? So this is like their interaction. It's not sufficient to break the lithium out from the salt cluster, right? So this is counter some of the argument that the binding energy correlates with solubility, yes, but not exactly, right? So steric effect is also important. One challenge of to get this heterogeneous structures is MD never is good for finding the equilibrium. So we generally will start from several initial structures, bigger clusters, small clusters, or random mix until we find the lowest energy, and that is like this size of the cluster at the end. So that's a trick. Anyone wants to look at heterogeneous electrolytes with heterogeneous structures have to try different initial conditions. Right, so this is my cell story. So I've been wondering, I keep asking the experiment group, I said, you have phase segregation, you have nanocluster in your solvent. Why your salt and solvent like cluster doesn't really kind of glob, like segregate, right? So so we see this, right? This is the salt and solvent cluster in this diluent phase. I forgot to mention, right? So this one don't like each other, and this one like each other, this one like each other very much. If you put all three together, what's going to happen, right? In the literature, people have been talking about the salt and solvent cluster dispersed in this diluent matrix. I just wondering why they don't collapse, right? But if you think this is like my cells, you know they don't collapse, right? This is a more stable structure. Our solvent actually is the peacemaker. It binds with the salt, and also like the solvent, so they will naturally should form some higher concentration layer at this interface and protect a solvation, like salt-solvent cluster, and in this matrix of diluent. And also, they are going to be this solvent in the diluent matrix, right? So that becomes an important feature. Right? So let me first explain why this is a mystery in experiment. So if we think we make the electrolyte, we make a high concentration electrolyte, and then we pour this diluent into it to make this so-called localized high concentration electrolyte, right? So if the salt-solvent cluster from their parent high concentration electrolyte, it simply dispersed, and we should not see any changes in this peak. And this Raman peak moving toward the right means there's more salt aggregates, right? And so one of what contributes to this is the solvent molecules eventually have some percentage in this diluent. So we leave like less solvent in this cluster to solve the salt, and we end up like higher salt concentration. And so that's characterized by all these pairs that Nidhi kind of talked about. isolated pairs, like aggregates plus. And then we do our MD, if we kind of go inside of this cluster, we see higher percentage of AGG plus, that's the aggregates, right? And you can also understand why you will have such a concentration gradient inside of this salt-solvent cluster. So this is a kind of a schematic that to show that traditionally we've been thinking about electrolyte as a homogeneous and very dilute to higher concentration, but it's still homogeneous. But this new localized high concentration electrolyte is a ternary electrolyte and with nanoscaled like a micelle-like structure. So it depends on concentration you can have, isolated or network. And we convinced the nature materials editor this is a material. It's not too much of a chemistry, but it's a really nanoscale structure, right? So we then want to understand if you have this heterogeneous structure in your liquid, what happens on the negative surface, right? So we're going to do our MD simulation. We look at all these clusters. This is not a schematic. This is schematic based on our counting. It's not just imagined schematic, so we counted all the coordination numbers, and we see that how in the bulk I told you we have these aggregates and solvent like clusters, and then and we have a diluent where the solvent have a percentage dissolved in that too, and then near the interface we still have the these salt clusters, aggregates. And you'll see then we start to see percentage of the ion and diluent half solvation structures. Right? This come back to my previous question. This binding energy of this diluent and that solvent with one lithium ion, it's almost the same, similar. But the problem is they cannot form, like diluent cannot form a full solvation structure. On the surface, it's good. You saw this in the morning that on the surface, you only need to form half solvation structure. So they can participate, right? So the diluent can participate. Because we also have fluorine species from them, so they will start to contribute to some fluorine species, and the ions will contribute to some fluorine species. And that is like more of like our counting of different species that get reduced from low concentration to high concentration to this localized high concentration. So basically at low concentration, we see some ion contributions, and with the increase of concentration, more and more of the ions start to contribute, being reduced. And then when you add this diluent and the TFEO also contribute a bit into our fluorine species, so you get more diverse like fluorine grains, lithium fluorine grains near the interface. And so we have to use this, right? If we have learned something, we have to make it useful. In this case, we also make it useful is to find a temperature that form the ACEI and with higher ion concentrations, right? We have to, typically if you change the temperature, you solvate the ions more, right? So you would think that this aggregates concentration will decrease with higher increase in temperature, right? Like this. So when this increase, right, I also told you this solvent can get into the TFEO diluent. So then we'll leave less solvents available to solvate the salt. So that will lead to AGG plus aggregates increase. Right? So you kind of have the Goldilocks like peak value right here. So we can use this peak value to form like ACEI. And then after you form this ACEI at different temperatures, the one that form at this temperature cycled much longer than other formation conditions. It's interesting, after we calculate this, we say if we keep increasing temperatures, right, you have more like a solvent dissolve, like mix with the diluent, and that will keep now finally you'll start to increase the aggregates again, salt concentration concentration in those clusters again, and then they also saw that, right? So, but we are not going to form yet at this temperature too many side reactions. Oops. Nope. Yeah. So this also gave us like more of ideas how do we kind of design electrolyte. And so we have a salt and solvent and diluent, right? So we want to push the solubility as high as possible, but of course not all the solvent will have such a high solubility. And this corner, we like the salt, the diluent and the salt have zero solubility, and so the diluent will never get into the solvation shell of these ions. We kind of also look at some other electrolytes and found this solubility play a very important role determine this nanoscale structures in the electrolyte. And so this is a collaboration with Astertech using Stony Brook. And this is a fluorinated solvent, like everything's fluorinated. Solvents fluorinated, additives are like fluorinated, this diluent are fluorinated. But because the concentration is not a 4 molar, it's about 2 molar. This is the maximum solubility we can achieve. And so they form you see more branchy type of salt clusters. And it's not a cluster, it's like branches of salt. If you add one additive, you break those branches, but you add another additive, you kind of collapse those branches, form a cluster. And that's because this diluent actually has zero solubility, and this one has some solubility, so they just act like a co-solvent, right? So here, we really want to plot and analyze our electrolyte in these 3 bins: salt, solvent, and diluent, based on solubilities. Right, so this is interesting. Another insight that obtained from the MD simulation is, this is the previous one I showed you, the concentration of the salt and the solvent ratio about 1 to 1.2. And this one is about 2 molar, so 1 to 3 ratio. And when we put this under charge, and you get to see a lot of the first layers, mainly the salt clusters, aggregates, and solvent. And because we still have a lot of free solvents available here, and this one we don't, right? So then diluent come to the surface. And so chemistry, compositions, interactions are all important. Yeah. So now, because there are so many different species near the interface, we have exhausted a lot of calculations, and okay, maybe we can train this a bit. So we want to do our DFT calculation with a bit of training. So we blindly train the reduction voltages for our first electrolyte, and then see if they can predict second electrolyte, doesn't, and retrain with second electrolyte. And we move to the fourth electrolyte here, and it worked really well. I don't believe it, and say it's like, well, you didn't train this, but because those diluent did not come to this double layer, and so they did not impact the reduction voltage that much, right? So we get another solvent, they really come to the surface, and then you have to retrain them again. So overall, after a few trainings, I think we predict the most complex electrolytes, with a few 1, 2, 3, 4 mix. It seems working, and I think the reduction voltage is not very sensitive to all these compositions, but a little bit more sensitive to the chemical, 1 or 2 chemical natures. That means that when we calculate our reduction voltage, this heat map, the area means the percentage of those species, the color means their reduction voltage from high to low. And so the reduction voltage is important, and this percentage is really important. So that's the story. And then we also want to do something about this, right? How do we take advantage of the electric double layer, right? So what do we learn? We learned that the ions and solvents all redistributed in these layers, not just the ions that get redistributed in the double layer. And so this is a recent paper we collaborated with Professor Song Lin's group in Cornell. So he's a chemist. He can make really magic molecules for pharmaceuticals. Want to make chiral molecules, which I don't understand those molecules. But if you think you make a reaction, you want to have the reaction, you introduce some intermediates some reactants that are chiral, and then the products, they can control the chirality left or right for that. If you're going to put those expensive molecules with chirality into the solvent, you need a lot of them. But if you make those chirality ions have a positive charged surface, those ions get higher concentrated near the interface, and they participate in this electrochemical reaction, and that can generate the chiral products in this. So they kind of tried this strategy for a series molecules they're interested. Right? So ions and cations get redistributed. We can use those higher concentrations to achieve chemical selectivity. Right? The other thing is to stop the bad reactions. Right? And this is like a example that we're going to reduce this. There's this molecule here, pechloram, and then it's kind of we want them in the bulk electrolyte. You get the two solvents that almost 1-to-1 ratio. But near the double layer, what you can see that the one with bonding with the cations get really higher concentration than the bulk values, right? Unfortunately, this one contributed to a proton reduction reaction. We start to give bubbles, and that's a sad reaction we don't want. We want this thing to be reduced. And so it turned on the change from DC to AC, we can dramatically reduce those ion-associated alcohols near the interface. And so you can change the frequency to tune the surface concentrations and change the prevent the bad side reactions. Right? So I hope I convinced you that the double layer is not just consistent of ions. There are many species in this double layer. The charge neutral species get redistributed as well. And we need new series, right? We need a new series that to describe the double layers for ions, non-ions, higher concentration solvent. So to the extreme that will go to the solid state. And so this one is we did using defect theory to look at the solid state electric double layer. So probably will not talk about that. So I hope by the end of this discussion that we have some ideas into how do we incorporate this more concurrently with all the DFT calculations, right? It's probably back to here, right? Reaction rates relate to the concentration and the K. DFTs really give us the barriers, but we should not forget about the concentration and the local environment really kind of change the energy reaction landscape. And my current workflow is all done separately. I hope I can learn something from you and can do this more coherently, right? So with that, I want to thank all the contributors to this, especially the postdocs and from MSU and Brown, and my collaborators doing battery work, and CSOE is fantastic, NSF Chemistry Center. There's so many chemists. I don't need to learn any chemistry. I can just study the interface. Thank you.